Hey, what's going on, everyone? It's Greg here. I just wanted to talk to you for a minute about elasticity and steak because it has to do with your problem number five. In steak, so I've drawn some springs here, and those are supposed to represent the crosslinks that are in the protein. And they're a little bit big, but you can imagine them smaller and throughout the steak, right? Okay, so what goes on in the problem? Okay, so we cook the steak. This is medium rare, something like that, and we cook it a little bit. And so what happens to the size, right? It shrinks. And so what happens to the texture of the thing, the strength of it? So it becomes then, steak becomes firmer. And why does it become firmer? That's the question that we want to understand. It becomes firmer for two reasons. So the first reason is the denaturing of the proteins. And so when they denature and come apart and then connect to each other, that creates more crosslinks, and that makes it firmer. And so can you guess the second reason? Well, the second reason is just because it shrank. So the steak shrinks and the existing crosslinks get smaller. Okay, so I just want to focus on the shrinking, and I want to give you an example. This is going to be the vegetarian example of what happens with shrinking and how you can figure out the elasticity increase when you shrink something and how much the elasticity increases. Okay, so let's say we have a block of tofu, all right? So it's some soft tofu. It's about 100 grams. It's a cube. It has side length L, and since it's a cube, the volume is L cubed. Okay, so I don't know if you know this, but when you want to fry tofu, you need firm tofu. But this is soft. This is soft tofu, and we want it to become firm. Here's a picture of some firm and fried tofu. So it'll look like that, but only if we make it firm tofu. And the way that you can make it firm tofu is you can actually squeeze out the water from the tofu. That's right, you can squeeze it out. So let's say we squeeze out 50 grams of water out of the tofu. So we originally had 100, and so now we have 50. And we're going to eventually want to know the volume of the final tofu. But if we assume that we have the density of tofu and water is the same, then we can also assume that the percent change in the mass is equal to the percent change in the volume of the tofu. Okay, so since 50 grams of water came out of the 100 grams of tofu, that means that we have half the mass of the original block of tofu. And if we make this assumption, then that means we know the volume of the shrunken tofu is 1/2 the volume of the original tofu. And as I said before, the original volume is L cubed. So now what we want to figure out is we want to figure out what the elasticity is. Or rather, how much of the elasticity grew. And so to know that, we use this equation of the week. Sorry, there should be a cubed here. And so the equation of the week here has L shrunk in it. And so to figure out how big L shrunk is, we need to compare the volumes, the shrunken volume and the original volume. And we know the original volume, as I said, and the shrunken volume you can write in terms of L shrunk. And so plugging this into here and solving, you'll find that you can figure out what L shrunk is in terms of L, and then you'll know E shrunk. You'll know E shrunk in terms of L. And then you can compare the original elasticity using the same equation, and you can figure out how much more elastic the shrunken tofu is. So I hope that was helpful. If you have any questions, please email me. Again, it's Greg, and have a wonderful day.